If you are searching on how to solve problems about statically indeterminate symmetrically loaded two-span continuous beams under a uniform load, this video is for you. This is a problem that can have direct link to our topic. A simply supported beam has a span of 12 meters. It carries a total uniform load of 21.5 kN per meter. To prevent excessive deflection, a support is added at midspan. The requirement is to solve for the following. Calculate the reaction in kilonewton at the added support. Calculate the resulting moment in kilonewton meter at the added support. And calculate the resulting maximum positive moment that will develop over its entire length. If we will draw the beam satisfying what has been identified by the problem, here's the figure. The resulting beam is statically determinate beam. Notice that for statically determinate beam, the number of unknown reactions are equal to the number of stability equations, which is also known as the equations of static equilibrium, which means that the problem can be solved and eventually the shear and moment diagram can be constructed. However, if we will provide additional support at the midspan to satisfy the condition made by the problem to prevent excessive deflection, the beam will become statically indeterminate, which requires tedious analysis. Since the equations of static equilibrium summation forces along x is equal to 0, summation forces along y is equal to 0, and summation of moment is equals to 0 will no longer enough to predict the response characteristics of beams of this kind. Remember that basic law of mathematics requires that the problem can only be solved if the number of unknowns are equal to the number of available equations, which is common for statically determinate structures. This is what we can observe for statically determinate beams, with a total of 3 reactions, AX, AY, and CY equal to the number of available equations, summation forces along x is 0, summation forces along y is 0, and summation moment equal to 0, which is also equal to 3. Since number of available equations are equal to the number of unknowns, therefore reactions AX, AY, and CY can be solved by applying equations of static equilibrium, and eventually the response of the beam due to the applied load over its entire length can also be obtained. In the graphical presentation of this response, the shear and bending moment diagram are being constructed. On the other hand, statically indeterminate beams have excess reactions that leads to more complicated analysis, like what we can observe in this figure, where excessive reactions were provided, vertical reaction at A, B, and C, and additional horizontal reaction at A, with total number of reactions equal to 4, which are greater than the number of equations available. Summation forces along x is 0, summation of forces along y is 0, and summation moment is equal to 0, which are only 3 equations. Because no loads are applied in the horizontal direction, horizontal reaction at the hinge support is equal to 0. That is to satisfy summation forces along x is equal to 0. Common mistake is to compare number of unknowns to the number of available equations after making the conclusion that AX is 0, since number of reactions reduces to 3. It should be clear to us that because summation forces along x is 0 will be subtracted as well to the available equations, which in return reduces also to 2, leading into a beam which remain as statically indeterminate, because 3 unknown reactions AX, AY, and CY are still greater if we compare to the 2 remaining equations. Summation forces along y is 0 and summation moment is equal to 0, since summation forces along x equal to 0 is already subtracted to the number of available equations as well. There are lots of classical analysis available as a solution for statically indeterminate beams. All of them requires additional equations that is usually adopted from elastic response or slope and deflections that we can combine to the equations of static equilibrium in order to find solutions to this kind of beams. Some of these classical analyses are the method of superposition, the force method, or the method of consistent deformation, and the 3-moment equation, but some may lead to tedious calculations if we carelessly pick a solution that will not simplify calculation. One of the available solutions that match up our current problem that will lead to simplified solution is the method of superposition. If a beam is subjected to several loads acting simultaneously, the total response at any point is equal to the algebraic sum of the responses caused by its load acting separately. To apply this method, we need to find a way to separate the loads acting in our beam. Actually, there is only one type of load in our beam, and that is the uniformly distributed load. We can have only additional load, by considering the redundant reaction, that is By, as load. Redundant because static stability only requires 3 reactions, which are non-parallel and non-concurrent force components. More than 3 reactions provided on a beam, therefore, will have excessive reactions that is referred to be the redundant reaction. The process in applying the method of superposition begins with removing the excess or redundant reaction to have a primary beam under the action of real load that will allow downward deflection at that point where redundant reaction is located. Since we remove the redundant reaction, we have to apply it back on our beam to compensate the effect and allow it to deform in opposite or upward direction. This beam is referred to be the primary beam under the action of redundant load. The formula to compute the deflection at midspan of a simple beam with a total length L under the action of uniformly distributed load applied entirely over its length is 5WL raised to 4 divided by 384 EI. The formula to compute the deflection at midspan of a simple beam with a total length L under the action of concentrated load applied at midspan is PL cubed divided by 48 EI, replacing the value of P into By. Since the reaction at the midspan By is acting as a concentrated load applied on the beam, will give us By L cubed all over 48 EI. I have already derived these formulas from my previous videos. See the link in the description below for reference. By applying the definition of the method of superposition, we will add the deflection of beam at midspan under the action of a concentrated load By, our redundant reaction, and the deflection of beam is still at midspan under the action of a uniformly distributed load applied over the entire length of our beam. Through this, we can write our compatibility equation, which can be comprehended as follows. The deflection of beam under the action of a concentrated load By applied at midspan, considered to be upward positive, plus the deflection of beam under the action of a uniformly distributed load applied entirely over its length, considered downward negative, is equal to the deflection of statically indeterminate beam, which is 0, since support is being provided at that point. After simplifying the compatibility equation, we arrive into an equation where By is the only unknown. Thus, after we carry out the calculation, By is equal to 161.3 kN. Using the equations of the static equilibrium, summation forces along vertical is equal to 0 and summation moment is equal to 0, we can now determine the remaining support reactions Ay and Cy, which are equal to each other since we have a symmetrically loaded beam. The shear and bending moment diagram can now be constructed. Shear at A is equal to the reaction at A, which is 48.4 kN, positive because it is upward in direction, therefore it is located above the neutral axis. Shear just to the left of B is equal to shear at A minus area 1. Area 1 is negative because it is acting downward. Since area 1 is equal to 129 kN, the resulting value for the shear just to the left of B is negative 80.625 kN. Therefore, it is located below the neutral axis. Shear to the right of B is equal to the shear just to the left of B, which is negative 80.625 plus the reaction at point P, which is equal to 161.3 kN. By is positive because it is upward in the direction, which results to 80.625 kN. Therefore, it is located above the neutral axis. Shear just to the left of C is equal to the shear to the right of B, which is 80.625 kN minus area 1. Still, area 1 is negative again because it is acting downward. Since area 1 is equal to 129 kN, the resulting value is negative 48.4 kN. Therefore, it is located below the neutral axis. Just to the right of C, shear to the right of C is equal to shear just to the left of C, which is negative 48.4 kN. We add Cy, which is upward, taken to be positive, equal to 48.4 kN. The shear force diagram terminates at 0 at point C. Since the load is uniformly distributed or constant over its entirety, We connect the points using straight lines to have the graphical presentation of shear over the length of our beam. We can now have our shear diagram, and we are now ready to construct the bending moment diagram. Accordingly, change in the ordinate of bending moment diagram is equal to change in area of the shear diagram, the very reason why we need to compute the area of the shear diagram, which also requires us to solve for the distances x1 and x2 in our figure. x1 will be calculated from the shear equation. The shear equation is being obtained from after passing a cutting plane that will cut the beam with a distance x1 from the left support. From the resulting free body diagram indicates that at the point of zero shear, there is always a value of x sub 1 that should be multiplied to the uniform load such that the resultant force is equal exactly to the reaction at A. Accordingly, we obtain x1, which is equal to the ordinate of shear diagram at A, 48.4 kN, divided by the intensity of the uniform load, 21.5 kN meter, after writing the shear equation. Therefore, x sub 1, after we carry out the calculation, will be equal to 2.25 meters. It follows that x sub 2 is equal to 80.6 kN divided by 21.5 kN per meter will be equal to 3.75 meters. Since we have already computed the distances, we can now proceed in solving the areas of the shear diagram. Area 2 is triangular area, therefore it is equal to 1/2 of base times height, where the base length is equal to 2.25 meters and the height is the shear at point A, which is 48.4 kN. Area 2 can now be calculated equal to 54.4 kN meter. Area 3 is another triangular area, therefore it is also equal to 1/2 of base times height, where the base length is equal to 3.75 meters and the height is the shear at point B, which is equal to 80.6 kN, resulting to an area equal to 151.2 kN meter. We can now find the ordinates of our bending moment diagram. From definition, the change in the ordinate of our bending moment diagram is just equal to the change of area of our shear diagram. We can now calculate the ordinates of our bending moment diagram. At the location of zero shear in our first span, maximum moment is being computed and the ordinate is equal to area 2, considered to be positive since this is a positive area. Moment at mid-span support at point B is equal to area 2 minus area 3. Area 2, which is equal to 54.4, and area 3, which is equal to 151.2, will yield to a ordinate at point B, which is negative 96.8 kN meter, since 151.2, the value of area 3 is greater than the value of area 2, which is only equal to 54.4. In our second span, at the point of zero shear, ordinate of the bending moment can be calculated equal to area 2 minus area 3 plus area 2. Since we are just following the definition that the change in the ordinate of our bending moment is just equal to the change of the area of shear diagram, the resulting value now is equal to 54.4 kN as well. And at the end of our beam, the ordinate of bending moment is equal to area 2 minus area 3 plus area 3 minus area 2, which is clearly equal to 0, which means that the bending moment diagram terminates at 0.